By the end of this decade, at a precise moment no one can yet predict, we'll receive the last signal from the Voyager probes. It'll be a digital whisper that'll take nearly 24 hours to reach us, traveling at the speed of light across 15 billion miles or 25 billion kilometers of cosmic void, then silence forever. But before that happens, we want to pay tribute with this video summarizing all the discoveries they've made and the emotions they've given us. Launched in 1977, when the world was grooving to the Bee Gees and Star Wars hit theaters for the first time, the Voyagers are dying. It's true. Their radioisotope generators lose 4 watts of power every year. At launch in 1977, each probe had 470 watts supplied by 3 generators containing 10 pounds or 4.5 kilograms of plutonium-238. Today, they're operating on about 225 watts, barely enough to power 4 scientific instruments out of the original 11. When the power drops below 200 watts, the probes won't be able to keep their antennas pointed at Earth anymore, and the signal will be lost forever in the cosmic background noise. The instruments have been shut down one by one, like lights in a house being abandoned room by room. But before they vanish into eternal darkness, we owe it to ourselves to remember what these 2 probes, no bigger than a compact car, equipped with computers packing 69 kilobytes of RAM, less than an email, and 8-track magnetic tape recorders, have accomplished. They've transformed points of light into worlds. They've discovered alien oceans, extraterrestrial volcanoes, planet-sized storms. They've photographed Earth as a pale blue speck of dust suspended in a sunbeam. And now, as they prepare for their final breath, they continue to amaze us from interstellar space, a realm they were never designed to explore. And all this with technology that today seems prehistoric, but has proven remarkably robust and perfectly suited. No frills to the job it had to do, and still does, in the hostile environment of interplanetary space. The record-breaking numbers. The Voyagers hold so many records, it's hard to list them all. They're the most distant human-made objects from Earth. Voyager 1 is over 15 billion miles or 24 billion kilometers away. Voyager 2 at 12.4 billion miles or 20 billion kilometers. They're traveling at incredible speeds. Voyager 1 is hurtling through space at 10.5 miles per second, 17 kilometers per second, fast enough to go from New York to Los Angeles in 4 minutes. They're NASA's longest-running missions, 47 years and still operational. They visited more planets than any other mission: Jupiter, Saturn, Uranus, and Neptune, plus 48 moons. They've discovered 23 new moons, 3 new ring systems, active volcanism on Io, oceans on Europa and Enceladus, geysers on Triton. But perhaps the most impressive record is the distance of their communications. Voyager signals, transmitted with the power of a 20-watt light bulb, travel for 22 hours at the speed of light to reach Earth. When they arrive, they're so weak, a billionth of a watt, that it takes deep space network antennas the size of football fields to pick them up. But let's take this step by step, because numbers tell a lot, but not everything, and they're woven into a story that must not be forgotten. The beginning. It all started in the summer of 1964 at the Jet Propulsion Laboratory, when 30-year-old aerospace engineer Gary Flandreau was assigned to study new trajectories for exploring the outer solar system. And Flandreau nailed it, discovering that in a few years there'd be an alignment of the giant planets that would allow a probe launched towards Jupiter to also fly by Saturn, Uranus, and Neptune, using each planet's gravitational slingshot effect to reach the next one, cutting the time to complete the entire grand tour from 40 to 10 years. But they had to hurry. This particular alignment only happens every 175 years, and to fully exploit this favorable moment, the probe absolutely had to launch between 1976 and 1980. Flandreau's study, published in 1965, caused quite a stir, and in 1969 led to NASA's first mission proposal called the Planetary Grand Tour. later canceled due to budget constraints. Then came the proposal to launch 2 twin probes, generically called Mariner 11 and 12. They wouldn't receive the names Voyager 1 and Voyager 2 until 1977. The first aimed at Jupiter and Saturn, and the second tasked with completing Flandreau's hoped-for grand tour: Jupiter, Saturn, Uranus, and Neptune. That same year, JPL proposed building the probes, continuing the design phase begun in 1966. But it wouldn't be easy. Back then, there were still many uncertainties about the obstacles a spacecraft might encounter crossing a region of the solar system that hadn't yet been explored yet. Some scientists, for example, thought the asteroids in the main belt were so numerous they'd prevent any vehicle from passing through unscathed. The Pioneer 10 and 11 probes, launched March 2, 1972 and April 5, 1973 respectively, were huge helps in understanding that the danger existed but was way overblown. They'd serve as pathfinders for the Voyagers. The Pioneers proved the journey to the outer planets was possible, but their capabilities were limited. Basic processors that didn't allow semi-autonomous operations, only 6,144 bytes of memory, basic scientific instruments. The Voyagers, launched in 1977 to exploit a planetary alignment that occurs every 176 years, were completely different machines. Computers reprogrammable in flight, 11 sophisticated scientific instruments including 2 TV cameras with multiple filters, ultraviolet and infrared spectrometers, magnetometers, charged particle detectors, and plasma wave instruments. Long story short, after 8 years of modifications to the scientific payload and engineering, Voyager 2 launched from Cape Canaveral on August 20, 1977, followed on September 5th by its twin Voyager 1. March 1979, Jupiter. Voyager 1 started photographing Jupiter in January of 1979 from 35.8 million miles or 57.6 million kilometers away. Closest approach came March 5, 1979 at 174,000 miles or 280,000 kilometers from the planet's center, followed by Voyager 2 on July 9th at 400,000 miles or 645,000 kilometers. While the Pioneers have provided images with resolution of hundreds of kilometers, the Voyagers achieved 3-mile or 5-kilometer details, revealing a dynamic and violent world no one had imagined. The Great Red Spot, known since 1665, turned out to be an anticyclone 15,000 miles or 24,000 kilometers wide, rotating counterclockwise every 6 Earth days, with vortices breaking off at the edges and smaller storms being swallowed up. The atmospheric bands weren't static structures, but rivers of gas moving at different speeds, up to 370 miles per hour or 600 kilometers per hour, creating vortices and turbulence at the interfaces. Voyager 1 discovered a thin ring system around Jupiter when the probe passed behind the planet and photographed the Sun through them. 3 main rings made of dark dust particles, completely different from Saturn's icy ones. But the most surprising discovery came on March 8, 1979. Linda Morbido, a navigation engineer, was analyzing an image of Io to calculate the probe's trajectory when she noticed an odd bulge on the moon's edge. Enhancing the contrast, a volcanic bloom 186 miles or 300 kilometers high clearly appeared. It was the first observation of active volcanism beyond Earth. But Io didn't have just one volcano, it had hundreds. Some were erupting liquid sulfur at 2200 degrees Fahrenheit or 1200 degrees Celsius. Others were shooting sulfurous gas geysers into space at speeds of 0.6 miles per second, 1 kilometer per second. The entire moon was a hellish landscape of lava and sulfur, with molten rock lakes as big as Lake Superior and mountains that collapsed and reformed within years. The discovery revolutionized planetary science. If a small moon could be so geologically active, what else had we missed in the solar system? But the real surprise came when scientists figured out the mechanism. Io is tormented by Jupiter's tidal forces. The giant planet stretches and squeezes the moon like a stress ball, generating enough internal heat to melt rock. This tidal heating became a fundamental concept for understanding other worlds, including those that might harbor life. And there was more. Io deposits a ton of material per second into Jupiter's magnetosphere, creating a plasma torus, a ring of charged particles surrounding the planet. This plasma generates electric currents of 5 million amperes connecting Io to Jupiter, creating permanent auroras where the magnetic field lines touch the planet's atmosphere. Basically, Io and Jupiter are connected by a gigantic electric circuit visible from space. Finally, as Voyager 1 moved away from Jupiter, the radio instruments picked up something unexpected: radio whistlers characteristic of lightning. When the probe looked at the planet's night side, it saw visual confirmation, flashes of light illuminating clouds from below. It was the first time lightning had been observed on another planet, but these weren't ordinary lightning bolts. They were energy monsters 1,000 times more powerful than Earth's, electrical discharges that could vaporize an entire city. And they weren't rare. Jupiter crackled with electricity constantly, with storms lasting months and producing thousands of lightning strikes per hour. Europa showed an ice surface crossed by dark lines thousands of kilometers long, with very few impact craters, sign of a geologically young surface. The data suggested the presence of a liquid water ocean beneath the icy crust, kept warm by tidal forces. Ganymede revealed itself as the solar system's largest moon at 3,273 miles, or 5,262 kilometers in diameter, surpassing Titan, which had held the record. Voyager 1 discovered 2 new moons, Thebe and Matisse. Voyager 2 added a 14th, later named Adrastea. Hey Curious Squad, before moving on, be sure to subscribe to our channel, clicking on the notification bell, and leave us a thumbs up so you don't miss out on our daily videos. Saturn System. Voyager 1 reached Saturn on November 12, 1980, passing 77,000 miles or 124,000 kilometers from the planet. Voyager 2 followed on August 25, 1981 at 63,000 miles or 101,000 kilometers. The pioneers had shown that Saturn had rings and moons, but the Voyagers revealed a system of unimaginable complexity. The rings, which from Earth seemed to be 3 or 4, turned out to be composed of hundreds of thousands of thin rings, some only a few meters wide. There were rings braided like rope in the F-ring, held in position by small shepherd moons. Prometheus and Pandora discovered by Voyager 1. Radial spokes rotated with the rings, defying the laws of orbital mechanics, probably caused by electrically charged particles levitated above the ring plane. Voyager 2 flew through the ring plane, recording hundreds of impacts per second from microscopic particles. The rings were incredibly thin. If Saturn were the size of a football field, the rings would be thinner than a sheet of paper. Yet they extended 175,000 miles, or 282,000 kilometers in diameter. Spectral analysis confirmed that they were mainly water ice, with traces of organic impurities giving them cream-colored hues. Titan, Voyager 1's priority target, turned out to be shrouded in an opaque atmosphere of nitrogen and methane 10 times denser at ground level than Earth's. Surface temperature was minus 290 degrees Fahrenheit or minus 179 degrees Celsius. To get a close pass of Titan, Voyager 1 had to alter its trajectory so it couldn't continue to Uranus and Neptune, a sacrifice considered acceptable to study the only moon in the solar system with a substantial atmosphere. Uranus, the toppled planet. Only Voyager 2 continued beyond Saturn. On January 24, 1986, after 8.5 years of travel, it reached Uranus, passing 50,600 miles or 81,000 kilometers from its cloud tops. It was the first time a human vehicle had visited this ice giant tilted 98 degrees on its axis, basically rolling along its orbit like a bowling ball. Because of this weird tilt, Voyager 2 had to complete all close observations in just 6 hours, compared to the several days available for Jupiter and Saturn. The planet itself appeared almost featureless in visible light images. a uniform blue-green ball caused by methane in the atmosphere absorbing red light. Only by processing images with extreme contrast techniques did faint cloud bands emerge. Winds were blowing up to 350 miles per hour or 560 kilometers per hour in the direction of rotation, despite Uranus receiving 370 times less sunlight than Earth. The magnetic field was tilted 59 degrees from the rotation axis and offset by a third of the planet's radius from center, a configuration never seen before, suggesting unique internal processes. Voyager 2 discovered 10 new moons, bringing the total to 15, all with Shakespearean names: Cordelia, Ophelia, Bianca, Cressidia, Desdemona, Juliet, Portia, Rosalind, Belinda, and Puck. But it was Miranda, the innermost of the 5 large moons, that stunned scientists. Passing just 17,560 miles or 28,260 kilometers away, Voyager 2 revealed an impossible surface. Canyons 12 miles or 20 kilometers deep, 12 times the Grand Canyon. Cliffs 3 miles or 5 kilometers high. Ancient cratered terrains next to geologically young smooth plains with chevron-shaped structures unique in the solar system. Neptune and Triton. On August 25, 1989, after 12 years of travel and 4.3 billion miles or 7 billion kilometers covered, Voyager 2 reached Neptune, passing 18,200 miles or 29,240 kilometers from its center, closer than any other planetary encounter of the mission. To increase data transmission speed from the distance of 30 AU, NASA linked the Very Large Array in New Mexico and the Parkes antenna in Australia to the Deep Space Network, creating the largest radio telescope ever assembled. Neptune revealed itself as a dynamic cobalt blue world due to atmospheric methane. The Great Dark Spot, an anticyclone as large as Earth, dominated the southern hemisphere. But the real surprise was the winds. 1,300 miles per hour, 2,100 kilometers, the fastest in the solar system, blowing opposite to the planet's rotation. How is this possible on a world receiving 900 times less solar energy than Earth? Neptune emits 2.6 times more energy than it receives, the highest ratio among all planets, indicating a powerful internal heat source, still not understood. A second storm called Scooter for its speed circled the planet every 16 hours. Methane ice clouds formed and dissipated in hours. The magnetic field tilted 47 degrees and offset 0.55 planetary radii from center, like Uranus, suggested these anomalous fields are generated in shallow layers rather than the core. Voyager 2 discovered 6 new moons: Naiad, Thalassa, Despina, Galatea, Larissa, and Proteus. It also discovered 4 new rings, including incomplete arcs that shouldn't exist according to classical celestial mechanics, probably maintained by gravitational resonances with the moons. Triton, Neptune's largest retrograde moon, orbits opposite to the planet's rotation, was the last wonder. Passing 25,000 miles or 40,000 kilometers away, Voyager 2 revealed a world at minus 391 degrees Fahrenheit or minus 235 degrees Celsius, with nitrogen ice polar caps, unique cantaloupe terrains, young plains with few craters. But the most spectacular discovery was the geysers. Dark plumes 5 miles or 8 kilometers high of nitrogen gas mixed with dust, driven by 750 mile per hour or 1,200 kilometer per hour winds. They were the first geysers observed beyond Earth. Io has volcanoes, not geysers, active despite Triton being one of the coldest places in the solar system at 38 Kelvin. The pale blue dot, the photo that changed our cosmic perspective. On February 14, 1990, Valentine's Day, Voyager 1 did something extraordinary. At Carl Sagan's suggestion, it turned around for one last look at home. From 3.7 billion miles or 6 billion kilometers away, 40 times the Earth-Sun distance, it took a photo of Earth. In the image, our planet occupies less than a pixel. a tiny pale blue dot suspended in a sunbeam, almost invisible in the vastness of space. It was a technically useless photo from a scientific standpoint, but philosophically, it changed everything. Sagan wrote words that still give us chills. Look again at that dot. That's here. That's home. That's us. On it, everything you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam. That photo, more than any equation or theory, showed us how small, fragile, alone we are, and how precious this tiny world we call home is. No wonder it's become one of the most reproduced and contemplated images in human history. The Interstellar Environment. On February 17, 1998, Voyager 1 surpassed Pioneer 10, becoming the most distant human object at 43 AU from the Sun. On December 16, 2004, it crossed the termination shock at 94 AU, where the solar wind slows from supersonic to subsonic speeds, colliding with the interstellar medium. Voyager 2 crossed this boundary on August 30, 2007 at 84 AU. The 10 AU difference revealed that the heliosphere isn't spherical but squashed, shaped by the interstellar magnetic field and the Sun's motion through the galaxy. In the heliosheath, the turbulent region between the termination shock and the heliopause, the probes measured phenomena never predicted. Magnetic bubbles 93 million miles or 150 million kilometers wide, created by reconnection of the solar magnetic field, a magnetic highway where charged particles could flow freely between the solar system and interstellar space. Stagnation of the solar wind with speeds dropping to zero. On August 25, 2012, Voyager 1 crossed the heliopause at 121 AU and entered interstellar space. Plasma density increased 40-fold from 0.002 to 0.8 particles per cubic centimeter. Galactic cosmic rays, shielded by the heliosphere, now hit the instruments at full intensity. The magnetic field direction didn't change as predicted, remained aligned with the solar one, a surprise that revolutionized models of the heliosphere interstellar medium interface. Voyager 2 entered interstellar space on November 5, 2018 at 119 AU, encountering different conditions, a more gradual transition with a magnetic firewall of hot plasma. In interstellar space, the Voyagers have discovered the hum of interstellar plasma at 3 kHz, pressure waves from distant supernovae crossing the interstellar medium like tsunamis, density variations indicating clouds and structures in the local interstellar medium, the fact that the solar system lies in a bubble of hot, rarefied gas called the local bubble, created by supernovae millions of years ago. The missed discoveries and regrets. For every discovery made, there's one that got away. Voyager 1 could have visited Pluto after Saturn, but the priority given to Titan prevented it. Today we know, thanks to New Horizons, what we missed: a complex world with water ice mountains, frozen nitrogen plains, and a layered atmosphere. The Voyagers didn't have the technology to directly detect exoplanets, which we only started discovering in 1995. They passed Europa without knowing that beneath the ice was an ocean with twice the water of all Earth's oceans combined. They couldn't confirm Enceladus's geysers that Cassini would later discover. Every mission is limited by the technology of its time, reflects Candice Hansen-Karchek, who worked on Voyager images. But it's frustrating to know that if we'd had just a more sophisticated mass spectrometer, we could have looked for biosignatures on Europa or Enceladus 40 years ago. The scientific legacy: how the Voyagers changed everything. The Voyagers inspired every planetary mission that followed. Galileo went to study Jupiter and its moons, building on Voyager discoveries. Cassini explored Saturn for 13 years following the trails left by the Voyagers. New Horizons visited Pluto, completing the grand tour that Voyager 1 couldn't do. Europa Clipper, launched in 2024, is searching for the ocean the Voyagers hinted at. But the impact goes beyond space missions. The Voyagers revolutionized comparative planetology, the idea of studying planets by comparing them to each other. They showed that geological processes aren't limited to Earth. They revealed that complex organic chemistry exists throughout the solar system. They proved that liquid water, an essential ingredient for life as we know it, isn't rare but common. Before the Voyagers, the solar system was in black and white, says Carolyn Porco. After, it was in high-definition Technicolor, and every color told a story. The future and the end. By 2026, 3 instruments per probe will remain. In 2027, the 50th anniversary, power will be about 210 watts. Below 200 watts, expected by 2030, it won't be possible to simultaneously keep the antenna pointed at Earth and the instruments operating. The last active instrument will probably be the magnetometer, requiring only 2.2 watts. After radio silence, the Voyagers will continue their trajectory for millions of years. In 40,000 years, Voyager 1 will pass 1.6 light-years from Gliese 445. In 296,000 years, Voyager 2 will pass 4.3 light-years from Sirius. Stellar orbits are chaotic on these timescales, making predictions beyond a million years impossible. The Voyagers might orbit the galaxy for billions of years or be ejected into intergalactic space. The golden records and aluminum and titanium structures will survive essentially forever, assuming the hypothesis is true that micrometeorite erosion won't exceed 1 micron per million years. When the Sun becomes a red giant in 5 billion years and vaporizes Earth, the Voyagers will still be intact somewhere in the galaxy, the last memory that humanity ever existed. They carry not just a message for hypothetical aliens, but testimony to what a curious species can do with $500 million, $5 billion in 2025 dollars, a bit of plutonium, and a lot of ingenuity. The Voyagers found volcanoes, oceans, geysers, storms, rings where we expected dead rocks and emptiness. They showed that the solar system is a laboratory for understanding processes operating throughout the universe. They've taken humanity, at least with our machines, to the stars. And as they prepare for eternal silence, they've already ensured their scientific legacy will last as long as our civilization, and their physical bodies much, much longer. Okay guys, is there anything you don't understand about what we've told you? If so, let us know in the comments. And if you want to learn more about asteroids, watch the video Voyager 3 and Voyager 4, or visit the section dedicated to this topic.